you for the invitation. Also, thank you for actually running this webinar. I'm a big fan of the webinar. I can never see one live because I'm usually in Australia. So the time zone never works out. It's like 2 a.m. In the middle of the night. So I always watch them on YouTube and I find them always fascinating and I learn so much from them. So thank you so much for inviting me. It's a big honor for me. So today, as introduced, I will talk about Neurodesk. So please ask questions. I'll try to monitor the Q&A box. And I have a demo at the end and also a specific block at the end where we can talk about questions. I can show things live. And as introduced, I'm a senior research fellow at the University of Queensland in Australia. And currently, I'm a visiting researcher at the Stanford Radiology Department in the United States. And that's why also the time zone is a little bit off for Europe, but it was the only way how we could make it work. So thank you so much for accommodating this time. So I want to talk today about the problems that we're covering, the solution that we're using, software containers, the architecture that we build the software around, how we're achieving reproducibility with this platform, and what we're currently working on. What's the outlook? What we want to do next? So I hope that's really interesting for all of you. Oh, and one little question I got in the beginning, what's this animal? This animal is actually our little mascot. It's a numbat, and a numbat is an Australian marsupial that's almost extinct. It mostly eats termites, and some people might have heard about it already. It's also Ubuntu chose it as their animal for the Ubuntu 24.04 release, so noble numbat. And we wanted something with N. So for Neurodesk, we chose numbat as well. And the numbat is really good at, as I said, it mostly eats termites, but it's also really good at just finding bugs, and we don't like bugs. So it's our mascot. So what are the challenges for scientists that I observe myself? I'm a neuroscientist, so I really struggled with all of these things myself. The first one really is non-reproducible workflows. And there's a really cool paper about this that I will show and go into more detail in a couple minutes. But basically, the problem is you run something again on another computer and you get different results. And that's really not great. Then another problem I faced was that I needed to run analyses on different infrastructure, on my notebook, on a high-performance computing cluster, on a cloud provider. And every time I had to install software, set it up, and I spent so much energy and time doing that, that it was really painful. And I couldn't do a lot of my research because this was such a bottleneck for me. And data management is not trivial. Organizing files, especially neuroimaging, and I'm sure other domains have the same problem. We have our domain-specific formats, like in neuroimaging, we have NIfTY and MINC files, and you need special tools to read them and process them and organize them. In neuroimaging, we have a great standard for this, which is called the Brain Image Data Standard BIDS. So we have tools to help people organize this. And I'm keen to hear what other people experience in other domains. How difficult is it to actually work with your specific data? And when you realize that, yeah, just Python doesn't do it because, yeah, you need quite specific tools sometimes to process this data. And our data sets are large. We sometimes deal with terabytes, we often deal with terabytes of data sets, sometimes petabytes of data sets. And a standard notebook doesn't do it. So that's why we need often HPCs. And then data storage and privacy. That comes back to the same problem. How do you deal with a UK biobank data set, which is multiple hundreds of terabyte, depending on what data sets you analyze from it? And how do you ensure that this data is securely stored? And how do you process this data? So our approach to this in our project is we bring the tools to the data. And I'll show how we do this in a second. So I want to dive a little bit deeper into this reproducibility problem that's haunting not just our field, I'm sure. Here is a really cool paper from Tristan Glatar and colleagues. And what they looked at is a fundamental library in Linux called glibc that does a lot of the numeric processing in code. And a lot of programs are compiled against that library and they're dynamically linked, which means that the cool thing is you don't need to bring your glibc all the time. You just rely on a glibc installed on your system. The problem is that, unfortunately, when you update this glibc, people improve sometimes things in this library. They make it faster, they make it more stable. But the problem is this sometimes delivers different floating point results. So here's an example. A software in our field is called FreeSurfer. This is quite an old version now, 5.3.0, but that's what I used in the paper. And then they used a glibc version of 2.5, which is installed in the operating system, and the glibc version of 2.18. And now the problem is that the floating point position changed. And you think, well, this is probably not a problem, right? It's like a couple digits after the comma, shouldn't matter. Unfortunately, it does, because we, and I'm sure other fields as well, we run long-running computations, so thousands of steps of computing steps. And the problem is, every physicist knows, errors accumulate. And the problem is that in this instance here, the difference, this is a difference between two data sets that are identical. The only thing that was done is they were analyzed with different glibc versions underneath. So the software was the same, the operating system wasn't the same. So just glibc changed. And now we're getting mean absolute differences here, and we get significant differences in the t-statistics. And this is purely produced by a change in glibc. So there's nothing else changed, data didn't change, the software didn't change. Just someone chose to update the glibc. And this can happen to a researcher on a high-performance computing cluster. Sometimes your HPC admins don't even tell you that they do that. So you might end up with computational noise that's really unnecessary. So the organic solution that I've seen in our field is that people just get multiple computers. So they have one computer where they experiment with things, they have a high resolution version installed, then they have like a long running study that runs like since 20 years, so they have a very old computer where exactly that software is installed and they're not changing it. Then they have a computer where a specific package was installed because it's really hard to compile and basically doesn't compile anymore because dependencies don't exist anymore. So this is really challenging. And it's not good, right? These multiple computers, like if one thing fails, it's just not great and it's not reproducible at all. So here's the second problem, this portability problem. And that's what I talked about earlier as well, where let's say you want to run your analysis on your notebook, on your lab workstation, or in a trusted computing environment, in a cloud provider, on a high-performance computing cluster, or even for us, we want to run the software sometimes on an MRI scanner. And basically, this means you're compiling the software every time you're doing this. And in some instances, you can't do it. So like I have software that has dependencies, and again, comes back to glibc, where I can't compile it on our HPC because the glibc on the HPC is so old that the software doesn't compile. It says, look, I'm not compatible to this anymore. So I can't install my software on this HPC. On an MRI scanner, what we often have to do is we have to completely rewrite the software often in C++ to get it on there. So this is really frustrating. It takes so much time to move between these platforms that people often don't do it. And that's not great because there is really a need for sometimes piloting things on your notebook, moving onto a bigger workstation, and then sharing it with other people, and then even moving to an HPC, and then in the end, translating it to the clinic. So what if there was a solution that could cover all of these platforms with one tool? And this is what we chose. We chose to build our solution on software containers. So I'm sure people here have heard about software containers before. I just want to explain it very simply. It's basically a box where you can put software in there, and the software has all its dependencies it needs. And that means we can have the software next to each other, it doesn't interfere with each other, and we can quickly move it to another computing system. So that's just a simple picture. Let's dive in a little bit more into technical details. What software containers are, sometimes people are confused because they say, oh, this is like virtualization. So it takes away things and it takes away performance. It is virtualization, but it's very smart virtualization. It uses a Linux feature or multiple Linux features called namespaces and C groups. And these features can isolate processes and dependencies from each other. And the cool thing is that it's very efficient. So you don't have a lot of overhead. There's not a lot of startup time. So if you used virtual machines in the past, you know, like you have a reserved amount of memory, you have a reserved amount of CPU, and then also it takes multiple minutes sometimes to start up this virtual machine. In a container, this is very different. Containers don't reserve things per se. They manage them nicely. So if your process currently needs 2 GB of RAM, it gets it. And then later, if it doesn't need it, it's not consumed. And also startup times, they are in the hundreds of milliseconds if you're unlucky. They can be really, really quick as well. They can be in a millisecond range. So really, software containers, and I probably can't overstate that, they have completely changed how cloud computing works. And it really enabled moving quickly through development and deploying it on different computers in the cloud. So why not use that in scientific software? And really what it's doing is it's taking these dependencies that are currently connected to the operating system, which then our software, our scientific software depends on. So this please see as scientific software. And what we do is we take these dependencies and we move them into this box. And then when we move this box, we have everything we need to run the software. And we can run it pretty much anywhere that has container support. And luckily these days, this is every major operating system. So on Linux, this is a native feature. So this is part of the Linux kernel. It works since 20 years, and it's really nice and stable. And really, Docker is probably the one biggest tool there that made it really easy to use this technology. But there were previous technologies that made that possible. On macOS, it's a virtual machine. Yes, so there's some virtualization involved on macOS, but ultimately it's very efficiently implemented as well, and you don't feel a lot of this overhead of a virtual machine running there. Same on Windows. Windows has the Windows subsystem for Linux where these containers run in, and it's pretty efficiently implemented. So what it means is, because we chose to run on containers, and some people criticize us for that because they say you shouldn't use a container, you should compile everything natively. And often we get this criticism from HPC people, and they see this from a very different angle. They see it from a performance angle, and that's probably true. We are not optimizing software for each computer chip, for each CPU. We're not doing that. We often have very generic builds, and we run them across different infrastructure. But for us, this gives us portability and reproducibility. So in our field, this is crucial. So now what's the architecture that we build around these containers? And this is really what Neurodesk is. So you see the community, neuro containers, and then you see our target environments. I'll start with the containers. So as I just introduced, containers take software and its dependencies and put them in containers. So we have the binaries, the libraries, VS Code. We have then like Python and then things that depend on Python that are installed in these Python environments. So we can tightly control what's installed in them. And then we have all these different software packages. Currently, we have multiple hundred of those. And then we have an accessibility layer. And this accessibility layer looks like a little thing, but it actually took us most of the work in this project, because what we do here is we make it really easy to use these containers. It's because when you dealt with containers before, like, you have to run Docker run, Singletary run, Aptainer run, and a lot of users are confused. So we just abstracted all of this away, and our software just behaves as if it was installed natively. And we do this with lots of wrappers around these containers. And we also help people to access these containers on different platforms. So, for example, you can use these containers on Linux. Obviously, that's a native feature there, but that works really well. So we build like a neuro desktop that we call that. So it's a full desktop interface that has everything installed, everything is set up, everything is configured. And we can take this desktop, run it through Docker, Podman, or our own virtual machine that we build on Linux, Windows, Mac OS. We can also run this in the cloud. And then we go into a lower, I want us to still show that one. We go into a lower level detail where we can now run this on an HPC cluster, for example. And we get like only a command line interface, so not a desktop. And the Jupyter Notebooks is also a cool way how we can interface with the software in like a computational notebook, and we can document what we're doing and how we're doing it and encode, which is really nice in terms of literate programming. And then, and this is probably less relevant for other fields, but in our domain, we have one vendor, one MRI vendor, it's called Siemens. They implemented an open interface to run containers on their machine. So we can actually now take exactly the same thing that we did in research, and we can take it into clinical environments and test it and see how we can translate these ideas into clinical practice. And that's really, really powerful. So we're investing a lot of energy on this as well right now. And then an important thing for us is the community. And that's why I'm here today. I want to show, hopefully, how we are doing this in the community. And I want to show how can maybe expand this to other communities. So I'm really keen to hear there if people think this could be useful for them as well. So our community is using our containers on lots of different platforms, and then they're also contributing back. They're saying, oh, this container is not working. There's a bug in there, or I need this container. So this is really crucial for us to keep this whole project sustainable and working. And this is really it. It's quite simple when you look at it and when you say it fast enough, but it took us a couple of years to build, and yeah, it definitely solved our problems in that we had in our group, but luckily it also helps a lot of other people across the world. So here I quickly want to show how this data workflow looks like for people using Neurodesk. So for example, we start with importing data, but you can start anywhere really. We have different platforms that are specific to us. So DataLad is like Git for data, and it came out of the neuroimaging field, but it's a general tool that basically manages data in repositories. Then we have Open Neuro, which is a data sharing platform in neuroimaging. OSF is a general platform that open science framework where you can share your data. So we support all of these platforms to get your data into Neurodesk environments. We also support XNet, which is a data repository for imaging data. And of course, every cloud provider that you can think of. So we simply use our clone for that. And then you can process your data with all the tools we have available. As I said, multiple hundred tools right now. We organize this data and we document these analyses. And here we rely on our BIDS standard, the brain imaging data structure. And we use Jupyter notebooks a lot because Jupyter notebooks are really cool, as I said, for documenting and for sharing what people have done. So one thing you can already do with our environment, you can build a notebook in one Neurodesk environment and you can send it to a collaborator and it will work identically. And that's really, really powerful. That was something that frustrated me a lot. I had a script, I was sending it to someone, and my script always assumed that there is something there, that people have to have either a container framework or something installed, and usually things don't work. And with our environment, that just works beautifully. And you can also then take these notebooks and put them, for example, on Google Colab, and they run there as well. Or you can then take the data that you prepared, put it out to Open Neuro or to DataLad or to the Open Science Framework or even GitHub. And then people can start from this again and build on top of this data, which is really cool. So to make this really easy, we invested a lot of energy on making these interfaces to users as seamless as possible. So this is the work of a PhD student in my group, Tui. She forked off an Electron app from the Jupyter Hub project or Jupyter Lab project. And we basically build in control mechanisms to control the Docker engine in the backend or a Podman or a virtual machine that we bring. So in the end, for a user, it's just a simple click, set open local Neurodesk. And then it starts it in a local container and it does it. And you also see there's connect to remote Neurodesk server. So we also make it easy to run this in the cloud. What people get then is a simple Jupyter Lab interface. And we chose that because it's a fantastic open source project and lots of people are familiar with it already. And we didn't want to invent anything new. So we just said, okay, well, this is a fantastic project. Let's build everything into this. So it's a standard Jupyter Lab with lots of features that we added. So for example, standard thing, you can do notebooks, of course. In these notebooks, we added, for example, visualization specifically for neuroimaging. We also built in a full desktop where we have all the software that people can think of, and it's just available on a button click, and it just works. Here is the specific visualizations we built in. So this is a new feature that a postdoc in my team, former postdoc in my team built, Corbinian Eckstein. So he developed a tool where you can just double click on a file in the file browser in Jupyter, and it opens up a full brain 3D interactive viewer, and you can just browse the data and look at it. Because for us, this is really crucial. We always need to process a step, look at the data, see if things worked. And the same is true for these notebooks. So here we also use, all of these things are based on an open source library, which is fantastic. It's a visualization library called NeView. And this also works in a Jupyter notebook where we can also interactively visualize things in a notebook. Then, as I said, this is the desktop. So it's what you would expect. It's a Linux desktop, has all the tools installed, so you can do whatever you want in terms of interactive computing, which is quite important for our field, and I'm sure others as well, where you need to look at images. So the important features is all software is ready to go. Everything is in containers, so we have no dependency issues. Because it's in containers, there's reproducible, so we're getting the same results. This whole container, and this is quite fascinating, is only 1.5 gigabyte in size. So it's a Docker container. And then every piece of software in there is streamed into this container using CVMFS. It's a CERN virtual machine file system developed at CERN. and it is used by CERN to distribute software worldwide. And we use it as well to distribute our software. And EGI plays a crucial role in this as well, because EGI hosts some of these distribution servers in Europe that we use for our users in Europe. And we support full graphical user interfaces. So now people often ask us, okay, how do you run on cloud infrastructure? And the challenge that we had there is we very early on said we want to be based on Kubernetes because Kubernetes seems to be the way to run such applications at scale these days. The challenge that we had is that we are running on a lot of research cloud providers. And they often run OpenStack. And OpenStack is fantastic, except when you want to run Kubernetes, because Kubernetes is still not well implemented in OpenStack. There is Magnum, of course, it kind of works, but then a lot of features are missing. It's not very stable. So we chose to go a slightly different path. We're using K3s. So very often what we do is we just get a virtual machine or a couple virtual machines. We install K3s on them. So K3s can also handle multiple nodes. And then we use Longhorn for storage abstraction. And then we use Argo to manage our deployments using GitOps. So we have all of our deployments worldwide. We run a couple deployments worldwide. So we have everything in a GitHub repository, and then Argo pulls that in. We even run some installations behind firewalls. So for us, this pull mechanism was quite important. And then we use Grafana, Prometheus, the standard stack to monitor what we deploy and how we deploy it. So maybe that's quite interesting for people, and I can elaborate more on that if needed. So uptake in the community. We currently have 3,700 active monthly users from over 70 countries in the world. We see this based on the statistics on our websites and how people access our software. Our container has been downloaded more than 41,000 times. It's used in multiple university courses with more than 100 students. We run this at the University of Queensland, Wollongong University, South Carolina, MPI Tübingen, King's College London, just to mention a few. And EGI, again, played here a crucial role. They're providing resources, compute resources for the researchers in Europe to run workshops like this and classes on EGI resources using Neurodesk. And we're also using it in lots of workshops worldwide and rely on either local infrastructure that people have, or we go professional cloud or commercial cloud infrastructure. So what is our sustainability model? Will we still be around next year? And that's really something we had to put in from the beginning to actually get our first funding. So we were funded by the Australia Research Data Commons, and was our first grant. And they wanted to see a sustainability plan. So we said, okay, we have grant funding. We still need that to develop new features. And we're lucky that we get co-investment, for example, from the National Imaging Facility in Australia. We're funded by the Chan Zuckerberg Initiative, the EOS S6 scheme right now. And we had lots of smaller grants as well. But then another pillar is community. We have lots of active contributors that we don't pay, that contribute their time to the project. We host our CVMFS servers, not ourselves, but we rely on open infrastructure, the Open Science Grid, again, EGI supporting us in Europe, Jetstream in the United States. So through this, we can run our infrastructure without having a huge AWS bill. And we also offer Neurodesk as a service for workshops. So if you need like Neurodesk for 3 days and you have 100 users on there and you want really a commercial grade solution, we partner with a non-for-profit, the Queensland Cyber Infrastructure Foundation. They can provide this with SLAs and everything that people need, but then that's out of our hand and it's done professionally. And we just get some share of that to sustain our open source developments. And then we also have support from cloud providers. So we have research cloud providers like AIDC. EGI has lots of federated cloud providers that they support us with. We have support from AWS. We had Google Cloud. We had Jetstream in the US. We had Oracle Cloud for quite some time. And we have a donation page. So lots of our users, they are so happy that they have a solution for their problems. They actually donate money to us so we can keep going. And that's really been a crucial enabler to do things and to keep infrastructure running. We invested a lot of energy as well to make maintaining easy. So for example, postdoc in my team, Josh, he built an interface that enables people to very quickly build a container. So if you use like Docker before, it's not super intuitive. So what we did is we built a graphical interface where you can just say, okay, I need that package, I need that tool, and just puts it all together, makes sure it's all nicely built, doesn't waste space and all of these things. And then it submits it to GitHub. And then GitHub automatically builds these containers. So a user can contribute to our project without installing anything on their computer. They go to a website, NeuroContainers UI, they say what they want, they put it in there, they submit a pull request. The pull request gets automatically approved by one of the maintainers and then automatically built through GitHub Actions, tested, and then released. So with this, we enable really people to contribute easily new containers, because that has been a major bottleneck for us. How do we get new software in there? And we really rely on the community to help us there, because we can't do it. We can't do it in our free time. There's so much software that we want to support that we need people to help us there. And then once the software is built, we deliver it through CVMFS, or you can also download containers. We have lots of different options, but I want to quickly show how the CVMFS works. And here we have about 500 gigabyte of unpacked software containers, and we have a Stratum 0 server, and then we distribute that through mirror servers called Stratum 1 servers. And here you see we have we have about 10 servers of these, but we have, for example, here a US server, we have an EGI server in Europe, and we have a server, for example, in Australia. And then users connect to this through a server called MaxMindIP. So it selects the closest server to them geographically. And then we also have some speed testing included as well. And then we pick the fastest server for our users, and then these software tools just magically appear. So now I quickly want to show how reproducible is our system. And I'll quickly go over this because it might not be super relevant for people, but for us, it was a one driving factor of this. So a PhD student, again, in my group, Tui, she took this original paper that I showed in the beginning, and she reproduced the non-reproducibility. And basically, these are two tools in our domain, FSL Flirt and FSL First. They run in consecutive steps. And then we compare them across two different systems. So FSL, you see, is our software. It's the same version. And then it's running on different systems with different glibc versions. And on one system, glibc is 2.3.1. On the other one is 2.2.8. And then Neurodesk container has quite an old glibc version with Ubuntu 16.04. And then they're running on two different processors, which is also quite interesting. So we'll see what that happens there. And we compare them. So the cool thing first is when you locally install the software and you have two different glibc versions, you indeed get different results. And that's interesting, but frustrating. Neurodesk, because it's in a container, glibc is identical. We're not getting this, which is great. So 100% reproducibility there. Now, in another tool, FSL First, again, local install, what we would expect. It's not reproducible. This is, in this case, is a dice score. So 0.16 dice is pretty high. So there's definitely a bit of a disagreement between pipelines, although it's the same data, it's the same software, just glibc changed. Now in Neurodesk, we are also getting something. And when you look at the scales, it's about 1,000 times lower than what we would get over here. But we wanted to show it because this shows one point, reproducibility only goes so far. In software, and I'll come to the explanation in a second, we traced every execution in these libraries. So in the local installation, we see what we expected. glibc is different, so we're taking different paths in the execution. So very quickly, for example, this floor function, you see it gets called many times, and it's quite different, unfortunately. So yeah, we're doing different things between different systems. Whereas in Neurodesk, we are doing exactly the same thing. So in software, we're doing the same thing. So now why is there a difference? The reason is we executed them on different hardware. One computer was Intel, the other computer was AMD. And different processors have different floating point precision implementations. So based on the effect size that we saw, and I quickly go back to this, so it's quite tiny, we believe what we see here are floating point differences between CPUs. And that's nothing we can control with containers because we are relying on the hardware that we run on. And if they have different implementations, that's what it is. So that's how far reproducibility goes, right? So we are reproducible in software, but then hardware we do not control. So now I want to show, and yeah, I have about 5 minutes left before we go into demo and questions. I want to show what we're currently working on, and hopefully this is also quite exciting for you guys. So first thing is, Neurodesk, and we're working on this currently to work with our collaborators. And what are these different collaboration models that Neurodesk allows? So the first one is this centralized collaboration. So we install one Neurodesk, for example, on our cloud infrastructure, on an HPC. So all users log in, the data is there, and they all collaborate on the same data. And we do this for workshops, for trainings, and also for consortia work, where they want to work on the same data set with different people. And that's been quite powerful. And we just published this in a paper in Aperture Neuro, where we go through these use cases a bit. And then there's also this decentralized collaboration. And I think that's really powerful as well, because researchers can just run Neurodesk on their systems, on their data, and they don't actually share the data, but everyone runs the same software. So again, this is really cool for consortia across different sites, where we can then only share the results. And often these could be like quite private, quite sensitive data. So this works super well. And because everyone is using the same software, everyone is doing the same analysis, these results can then be nicely aggregated and then understood on a higher level. And yeah, this data privacy assurance is definitely something that was the driver for this. Now, another thing that our platform enables is interactive papers, because when you think about it, you write your analysis in a notebook, you could share this with your paper. And then if anyone else wants to run it, they can. They don't have to go through hours of setting up software. It just works. So we're really eagerly looking at the space of reproducible papers, re-executable papers, and see how our software solution can help these platforms to deliver that. So we'll see what comes out of these efforts. And we're also going this direction to enable really this publication lifecycle. So this is another paper that was just published from a postdoc in my team, Michelle. She put together a great paper on showing, okay, how do we make this whole citable, trackable, and put this into the scientific literature. So every one of our containers has a digital object identifier, so you can cite it, which is very nice. Then we link it to data. Then our pipelines, our workflows, they also have DOIs. So you can then really say, I use these 5 containers with a DOI, I use this workflow that someone else built, and then you really have these results in an interactive paper, and you can share it with your reviewers, with your colleagues, and people and the readers of the paper. They can really go and know exactly what you use. They don't have to guess what version of a certain software you used. And often it's really not feasible to document all the software you use in a paper, right? When you think about our computational stacks today, we sometimes have hundreds of tools, and sometimes you're limited still to 40 citations, which is stupid, but that's what papers do. So you often can't acknowledge the software that you're using, which is really frustrating, because scientific software is the backbone of research. It is research infrastructure, but very often it is omitted from papers. And scientific software developers, they really struggle to get basically seen and get funding for these things. So very often this is done in their free time, and we need to change this. We need to make research software more visible, and we believe that through proper citations, this can happen and should happen. So another big thing that we're working on right now, and we're putting together a paper on this right now, another postdoc in my team, Moni, is currently working on that. She's working on interactive examples, because we want to give people an easy way to get started and show what they're doing with Neurodesk. And I'll show this live in a couple of seconds, but what we're basically doing is we are collecting Jupyter notebooks with all the analyses and everything in them, and we execute them automatically on cloud infrastructure, again, EGI being one of them. So that's how it looks like. You can see it on a website, which is Jupyter Books, which is a fantastic project as well. And then you can say, oh, I want to run this interactively. And you can run this currently in America, or you can run this in Europe. So Europe would run on EGI infrastructure. And then people can go in and they can change parameters. And we believe this is really how learning happens, because just showing someone things is often, they believe they understood it. But then where really the understanding comes in is, okay, now let's take my data. Let's put it in. Let's see what fails. Let's change a parameter. Let's run it again. And these interactive learning, this is really something we believe is currently not really available with a lot of tutorials. So we want to build this out as a community resource and invite people to commit and contribute to this. And yeah, then you get this interactive environment, and yeah, it's fully reproducible, which is just cool. And again, as I said, in Europe, this runs on EGI infrastructure. Last thing, neuroimaging coding agents. I mean, I guess some people will hate it, some people will love it. We are very neutral to this. So neuroimaging coding agents, I believe they can be a big game changer for people who can't code. So psychologists who don't have a formal background in coding, they often struggle with this. And this is how they need to analyze their data. So we believe that in our environment, we know what tools are available. We know what tools can do. So if we expose this information to an AI, to a large language model, we can actually code analyses. And also we have these example notebooks that I mentioned earlier, right? So we know how a good analysis should look like. So if we feed this information into a scientific coding agent, we can actually produce code that's very, very free of hallucinations because we ground it in real data, in real work. And it's following good standard practices. And it really helps people to accelerate their work. What's important for me is they are fully in control of what we're doing. We're generating a notebook, and in this notebook, they can see exactly what's been done. They can change it. They can execute it. They are in the driver's seat. We are just helping them to give them code faster and hopefully better as well than most humans or that many people could write it. And this is something we're currently actively developing, and we're looking for funding for this. So if people are aware of anyone who wants to fund this, please let us know. This is currently our free time project. So the last thing I want to go into is, and this is really where I invite you guys from the EGI community. I think if this works for neuroimaging, couldn't we do this for all scientific domains? Are we the only ones struggling with these problems? I'm not sure. I don't know. So one thing we would love to do, and we have a domain ready for this, sciget.org. There's not yet a lot of content there, but what we have done in the last month is we refactored everything in Neurodesk that's domain specific and that's non-domain specific. And we separated these things. So everything that's neuroimaging domain specific is in neurodesk.org. Everything that's non-domain specific, it is in sciget.org. So our cloud infrastructure, how we build containers, how we do all of this, we would like to see if this would be useful. So if you are part of a scientific community that would love to be involved and help, of course, we need funding for this, and build this as a community, then I think that would be really wonderful. And we would be more than happy to support, but we cannot drive it because we don't understand what other domains need. But if this is something you want to help us with, then you're very welcome. Please get in touch. Last thing, really, if you want to know more about Neurodesk, we have a Nature Methods paper that was published 2024. So there's a lot of details in there, and you can read up on that. And Neurodesk current contribution and funders. So we are supported by really lots of people. I just want to mention them here. In Australia, National Imaging Facility. In Europe, EGI, AIDC in Australia, Chan Zuckerberg Initiative. We rely on Jetstream Cloud in the United States, and we rely on all of our contributors worldwide. And you see, it's currently quite an Australia-focused base, but we are hoping to extend this to Europe. If this is useful, please help us contribute. We can't do this alone. We're building it for the community, with the community. And in summary, where is EGI supporting us with Neurodesk? So first, and I mentioned it throughout the talk, but EGI is really a keystone for us in Europe. So without EGI, Neurodesk wouldn't work well in Europe because we cannot fund servers like our CVMFS infrastructure. We do not have funding for that. So EGI runs, for example, our Strat1 servers in Europe. They are also allocating resources to us through the CESNet MCC, which runs our Neurodesk Play server. So where, for example, our example notebooks run. And they give us about 110 CPU cores, about 380 gig of RAM, and 3 terabyte of block volume, which we need to run the service. And we also have a service level agreement, which helps us to make sure this is all reliable and good. And yeah, we're consuming resources, which is very nice that we can do this, because if you would have to pay for this on a commercial cloud, we couldn't do it because no one funds software projects for maintenance. Everyone wants to build something and they give you money to build it, but no one wants to support ongoing costs. And I'm very happy there for EGI to support us there with cloud resources. It wouldn't be possible without them. So last slide, really, that's the team behind the scenes. lots of people from PhD students, postdocs, software engineers, cybersecurity engineers that work on this platform to make it possible. And now we are ready for live demos and questions. So first thing I want to do is I want to look at if there are any questions. And then I can show a couple of things. So Q&A.
We do have
Okay.
a question from Marcel Luz.
Yes, Marcel Lewis wrote a question there. Are these calculations done in double precision? And that was, I'm sure that was earlier from the slide where I showed like floating point precision. So it's hard to say. A lot of them are in double precision, but sometimes people use less precision to save memory and compute. So yeah, it's a huge software stack that's pretty much very hard to trace if everything is double precision. I hope that answers your question.
Is it answering the question, Marcel? You can talk.
Yes, thank you. I was just curious because I saw these differences, and well, I know from experience that if you use single precision, that differences like even 1% are not uncommon. So
Yes, absolutely right. Exactly. So I think that's what it most likely is. Exactly.
yeah.
So yeah, exactly. So these things we believe come from that. Okay, cool. So while we wait for more questions, I want to quickly show how easy it is for users to use Neurodesk. So here I'm on a MacBook and it's an M1 processor. So most neuroimaging software wouldn't run on this. So we use Rosetta 2 for emulation, but I'll just close the chat for now in the Q&A just to make sure this is all good. So this is our Electron app that I mentioned in the talk. We can basically just say, okay, open a local Neurodesk. This will now talk to my Docker in the backend, and it will start the container. So what you see here is we are not confusing the users with many commands to run because a lot of our users are not so technically trained. So if we tell them run Docker, they might get confused. So here we are now in this Jupyter Notebook environment. And the first thing is I have an example notebook here that I can execute. So run all cells. And we can quickly go through this notebook. So one thing we did for our notebooks is we're using an HPC system called module, LMOD. And this module system can basically load software. And that's how we make it explicit to people. So we say, if you want to use this software called FSL in a certain version, well, you need to load it. And that's how we ensure that people know what software they're using. They can also specify it without the version if they want to, then it will just load the latest version, but we always encourage people to tell us which version they use. And then here the output would actually tell it which versions it would use. And then these tools that are in that container, they become magically available. And this is like when we execute BET. This tool now comes from this FSL container. But here you see the user doesn't have to understand that. The user just says what they want, and it just magically works. And that's really, I think, the key to the success of the project is we did not confuse our users with technical details that they don't have to know. So basically, run the tool, load the container, and it just works. Then here, we're just loading more software, right? So if you would have to install this software, this would have taken you hours. And that's just 3 really easy to install software pieces. We have software that's not easy to install, that's not easy to compile. And we download some test data, and then we can just run a pipeline. So here we're supporting, I mean, other domains have probably similar systems. I think there's Nextflow for genomics. There are general workflow languages. We use NiPipe and probably soon Pydra, which is like a neuroimaging specific workflow engine. But it has a lot of these abstractions built in. So we can say, okay, I want a brain extraction. This is the input file. This is a parameter. Just run it. And then it does. It parallelizes across CPUs. And then it just processes the data. And then we can visualize it. And here I just show like how you would do it in a standard notebook. You would use like matplotlib and you plot it like this. But the problem is when I click on this, nothing moves. I can't really check the data. So yeah, I can see something worked, but I'm not sure if it's great. So this is now where NeView comes in. NeView is this wonderful visualization library. And now look at this. It's interactive. I can actually look at my data, which is so important for us because I need to see that the brain extraction here actually didn't do a good job. So this should be a temporal lobe, but it's missing. It's been cut off by the brain extraction tool. So And then, yeah, we can just run more of these pipelines. And yeah, you see this is still running here. So I just saw there's another question in the Q&A. I'll quickly have a look at this. Tejasvi Ravi. Hi, there are a wide variety of softwares within Neurodesk server. Is there any option to switch between software seamlessly? For example, I use FSL for thresholding, and next step would be FreeSurfer for parcellation. Is there any method that calls the imaging application simultaneously? So yes, exactly. So I should quickly show this on the terminal. So just show me exactly your example there. So you said you have FSL. So right, let's say for thresholding, BET is an FSL tool. It's not there. So what you do is you load FSL. So now FSL is there, and there it is, FSL 6078. I didn't specify a version, so it loads the latest version. And now BET should be there, and there it is. So now FreeSurfer, let's say Recon All, right? Recon All is a FreeSurfer tool, and you see here that Recon All is not available. Now I can say, okay, module load FreeSurfer. This will take a second, and now there it is. Now we got FreeSurfer 8.10, and now if I ask which Recon All, then I get, yep, it's coming from this container. And then that's how you can use them simultaneously. So now you have FSL, now you have FreeSurfer, and you don't have to worry about anything. You have the version specified, you can run these tools, and I can quickly show while we're here how this works. The magic that we're doing, and like people say this is stupid, but if it works, it can't be stupid, right? So what we're doing here is it's a wrapper script. It's a wrapper script that then calls into our Singularity container. So I argue that typing this for a user is not feasible for most of our users. Whereas simply typing Recon All and things to work, this is feasible because they can now follow normal tutorials. This looks scary. And just typing Recon All is fine, right? So that's what we chose. We chose to make it really, really easy and enable people to do their work without getting in their way. Tejasvi, does this answer your question?
Yes, Steven. Thank you so much.
Okay, wonderful. Yes. Thank you so much for the question. That was great. Okay, we have about 8 minutes left. I quickly want to show the Neurodesktop. So Neurodesktop, this is really now, let's say you want to explore data, and sometimes it might not be the most reproducible thing to do. So there's actually a little bug on macOS. When you open it initially, the screen resolution is really high, so you have to quickly do a force reload. So here we have this interface. So now you see we have all this software. And yeah, these are all the applications that are available. So we categorize them for people in different categories, because some people, they come to us and they say, oh, I want to do image registration, and they don't know what tools can do image registration. So we give them a selection. We say, well, ANS is fantastic for that. FSL can do it, Min can do it, NiftyReg can do it, Slicer can do it, SPM can do it. So, and then also, for example, image segmentation. Again, FSL can do it. ANS can do it. So our tools can be in multiple categories, and we explicitly made it that way because we wanted to give people a selection, a pre-selection of tools. And here you also see an interesting thing is, although it's called Neurodesk, we had already other domains reaching out to us, like body imaging people who do fat segmentation in the whole body. We had cryo-EM people reaching out to us and say, can you put our cryo-EM software in there, like Raelion and Topaz? Because we don't have anything like this in our domain, but we would really love to do that. And that's also where like the idea of SciGet got born, because we saw there is a real need. That's probably the only things right now that are not, spine imaging. So spinal cord toolbox, we have a bit of things there. But yeah, so that's really, we just got some molecular biology tools. So yeah, so currently we're expanding this, but we would like to clean this up a little bit and keep Neurodesk, again, back focused on neuroimaging, and then move all of these things into separate projects. But we're really waiting for the community to drive this effort, because as I said, we can't do it. We are already stretched with what we're doing with Neurodesk. So this is nothing we can lead, not something we can do in our free time. So we need funding, and we need support for that. So, okay, this is running things locally. I'll close that here, and then I'll show something else. So let me grab a browser. So the easiest thing to get started with Neurodesk is going to our website, neurodesk.org. And again, a big shout out to our team that just redesigned this whole website, really led by Michelle, a postdoc, and my team. She did a lot of effort to make this website a lot more usable because we came from a developer angle in the beginning, and now it's a lot more user-facing. And you saw as well that we recently won the Technology Platform Award in Australia as the best technology platform. So I just saw there was another question. I'll quickly answer that before I go into the next block there. Marcel, are these modules loaded on the fly from a CVMFS server, or are they already present in a container image? So Marcel, all these things that I showed, they are loaded live from a CVMFS server. However, we have a fallback. So if you're not connected to the internet, or you can actually choose not to be connected and download things. So I quickly show that because we get this question sometimes. So in our settings in our app, you can go to settings and you can say container mode, stream or download. If you flick this to download, what will happen is when you're connected to the internet, it will download the container to your computer and it will stay on your computer. And the cool thing is then you can use the software in an airplane or when you're not connected to the internet. So it might make sense to switch that to download and download a few of the packages you really need. But be careful, these packages can be huge, like FSL is 10 gigabyte, FreeSurf is 20 gigabyte. So that's why we don't have it as a default, because we had that at the beginning and people complained that the hard drive is full all the time. Yes, because they downloaded 900 gigabyte of software and most hard drives are full at this point. In today's computers, right? MacBook, where if you're lucky, it comes with a terabyte, and that's quickly filled up. So that's why we stream everything. But then also, once it's streamed once, we cache everything in your local disk. So every piece, every software you called will be cached once you download it once. So that's another thing we do. But yeah, for reproducibility, we give people this option. I hope this answers your question, Marcel. Thank you so much.
Yeah. Thank you.
That's great. Okay. Good. Okay. I want to show 3 minutes left. Examples. So this is something I'm really excited about. Here we can basically go in here and say, okay, show me a basic NiPipe pipeline. This is what I showed earlier on my computer. So here I can show and I can look at these things and see the results. So this is just a standard website, right? So here it's not interactive. I can't click on anything, and I can't change anything. But if I go on this little rocket and I say run in Europe, EGI magic happens. So this is running now in Prague on SESnet servers. It's running our K3S setup. It's running Kubernetes, our small Kubernetes. So you see, this is our Neurodesk Play server in Europe. It starts a pod for the user. We authenticate via GitHub. I already did that previous to the session, so I'm not wasting time here. It's starting it up. And now I'm getting an interactive computing environment where I can modify all of this. I can put my own data in there and I can learn. I can interactively learn. And I think this is really a game changer to training. So see what it's doing now is it's cloning the GitHub repository with our example notebooks into that instance. That takes a couple seconds. And then once this is there, it should open the notebook. Let's see if it works. Live demos are always challenging, especially with cloud infrastructure involved. But here it is. And here's my notebook. And this is the one that I had earlier on my computer. And now I can run the same thing. I can run it and I should be able to get all the results there. So this is something, we're currently building out and writing the paper. So I hope, there's something good to show. Good. That pretty much brings me to the end that I had planned. There's 1 minute left. So if there's any more questions, please ask it now. And otherwise, thank you so much for attending. There's one more question, Q&A. Thanks for the talk and demo. This is very similar to our IceCat analysis environment, but quite a bit smoother. So I got lots of ideas. Okay, that's wonderful to know, Carl Frederick. I haven't heard about IceCat. So I'm keen to hear what it's doing. And maybe there's some synergies we can use there. So you could maybe get one of the first SciGet communities that we can port your software into there. That would be great to hear. So please reach out.
Yeah, it would be quite interesting. So what we do is that we run radar systems that look at the upper atmosphere of the Earth. And we are also EGI users and collaborating in EGI projects. So we provide a similar Jupyter image that can run on the EGI Jupyter Hub or on our own systems.
Yeah.
But So one main difference is that our image gets quite huge,
Yes.
but I would like to change to distributing the software on CVMFS right away.
Yes. Yes.
So you said you build your software automatically on GitHub and it gets deployed automatically on CVMFS as well. Or?
Yes. Correct.
That's kind of a build pipeline we should look into.
That
I
would be
suppose
great. Yes.
it would run on any GitLab or GitHub instance apart from GitHub, or
It's currently based on GitHub, but yeah, it
Yeah.
could be reported quite easily. Yes. So if you look in our GitHub repository on here, you find everything. So the repository there is called Neurocontainers, and we use GitHub Actions heavily because that was just something that was available to us. Yes.
Yeah. And then I have one more question about this Electron app that you provide.
Quickly, I just want quickly one addition to yours. So you mentioned the EGI has a notebook server, and the good thing there is that the CVMFS is already included there, so that works.
Yeah.
The problem that we run into is, so we can't run our things on there because we are using Apptainer on top, and that needs a user namespace that's not enabled on this one. So we're trying with the EGI team to get this to work, but that could be something, if you need this as well, that would be amazing because then we could use this notebook infrastructure as well, which would be fantastic. Yes, but yeah, the problem is, running Apptainer in Kubernetes needs a little bit more work. And yeah, that would be cool to solve that. But yeah, you had another question.
Yeah, it was about this Electron app that you showed and talked about. So does it always run the Docker image locally on the user's computer, or can it actually interface to one of these?
Can also, exactly. So
services?
here, if you click Open Local Neurodesk, it requires Docker, it runs locally, or it runs Podman or our own virtual machine. And here, connect to remote Neurodesk server. So here you can say, play Europe. And then again, this is the EGI server. So I'm now connecting, and it asks me for my GitHub credentials, which I can.
So that would have been my next question, how to authenticate, but it then goes to the normal authentication for the system.
Correct. Exactly. So yeah, I didn't log into this here, but yes. I won't show it now, but yes, exactly. You log in and then you get the same thing basically, and it's connected on a remote server. So again, we made this really, really simple because our users, they don't want to waste time with these things. Yes. Okay, cool. Thank you so much for these remarks. So I have a look at IceCat. That looked really interesting. And then let's connect in the background and let's work on this in the future. That would be great.
Also, you mentioned, Steffen, you mentioned there was you intending for this new collaboration for other community, and I guess ASCAD can be one very good example, and to collaborate to testing in radar science.
Yes.
Yeah. So, and Carl Patrick, I can keep you contact with Steffen, maybe.
Yeah, I'm not sure I got the email address in the invitation, but if you can send it to me, it will be fine.
Yes, I will quickly send it in the chat as well. Okay, that's the best email to reach me.
Yeah. Okay, thank you so much. It's so exciting, and thank you, Steffen. That's excellent talk and excellent discussion. And we hope you have a very nice day. And thanks to all our audience today to join us. It's so very late in Europe already, but hope you have a good evening and enjoy the talk as well. And also thanks to Federico work behind the scene to enable everything work smoothly. With this, I will thank you, everyone, and see you next time.
Thank you, everyone. Bye.
Thank you, Steffen. Hope we can invite you back soon to give us a new updating of the development.